Hello. This presentation will be covering how perspective transformations work. This is part one. Part two will come in a couple lectures. For part one, we're not going to do depth information correctly. We're only going to do XY positions on the screen. We'll see how that works. We'll get representations for that with 4x4 matrices, and then later presentation will discuss how to get the depth correct. So let me recall a couple things here. We had orthographic projections we already covered. So orthographic projections were covered in the last presentation, and these basically project at right angles onto the view screen. And this meant that there was no perspective, and the size of an object did not depend on its distance from the viewer. So let's draw a picture of what I mean by this. We've got the viewer, which I'll draw as a little stylized eye here. This is meant to be an eye or a camera. And by convention, the viewer will be sitting at the origin and looking in the negative z direction. So here's the negative z-axis pointing up. We have some sort of top view here. And there's some objects sitting here in space. So maybe there's a F shape, maybe there's a triangle, and there's a view screen. And we sort of mentally were thinking of the objects in space being projected onto the view screen at right angles. So the F, the vertices on the F project straight down onto the view screen. The vertices on the triangle project straight down onto the view screen. And so the size that the triangle occupies on the view screen doesn't depend on how far it is from the view screen. In this way, there's no perspective. And as we saw in a previous presentation, the matrix that does this kind of thing is just literally a scaling, axis-aligned scaling, and translation. For perspective, we have now things are projected in the direction of the viewer, and things, the size of things on the view screen depends on how far it is from the viewer. So it's the same kind of setup. We've got the view screen. We've got the viewer sitting at the origin. So again, draw a little stylized eye here. Here's the origin again. And here's the negative z-axis again. And we'll put the same objects here. There's an F. There's a triangle. And now what we do is when objects are projected onto the view screen, they're projected in the direction of the viewer. So for instance, the bottom vertex on the F gets projected down and lands here on the view screen when it's being sent in the direction of the viewer. This vertex on the F lands here on the view screen, and so forth. So everything is projected to the view screen, but not at right angles. It's projected towards the position of the viewer. In this case, the viewer is at the origin, so everything is just projected towards the origin. It makes the computations a little extra simple to have everything at the origin. And in this way, if the triangle moved closer to the view screen, it would occupy more space on the view screen, just by virtue of being closer to the viewer. If it moved further away, it would occupy less space on the view screen. And by this method, we will get the appearance that things that are farther away look smaller than the same things up close. So we'll do the mathematics on this on the next board. So to get the correct formulas for the perspective transformation, we need to be more precise about where the view screen is and so on. So let's draw the picture again. So here's the viewer. This is the eye position, or the viewer. And the viewer is sitting at the origin. And let's draw the x and z axis here. So here's the x-axis. Here's the z-axis is pointing downward in this view. So this is a top view, with the y-axis is pointing out of the board towards your towards you as the viewer, right? So we'll put the view screen, I'll put the view screen right here at, this will be the z equals minus d plane, is the view screen. And so this line represents the plane parallel to the xy plane. That's where z equals minus d. So this view screen is distance d from the viewer. And we've got some point up here. So here's some vertex, which I'll call u. And it's got xyz coordinates, which I'll call xyz. And now, in particular, here's the value z here. Here's the value, well, x is down here. And we're going to project it for perspective transformation towards the viewer. So we send it in a straight line down to the viewer, and we hit some point v here. Okay, and we want to have a formula for v in terms of u. So let me give v some name. Change it to be black. So v will have components x prime, y prime, z prime, and it will sit right here. So we want to get formulas for x prime, y prime, z prime. So we want formula for v, that is formulas for x prime, y prime, and z prime. Well, pretty clearly, z prime equals negative d because it's sitting on the z equals minus d plane. And we use the method of similar triangles to get the rest of this. This distance is x. This distance is negative z because we're going from 0 down to the value z. So z is negative in this picture. Negative z is positive. And this distance is already labeled as d. And this distance is x prime. So by the method of similar triangles, x prime over d is equal to x over negative z. So that gives us that x prime equals negative d times x over z. And similarly, y prime equals negative d over y over z. So v is going to be the point negative d x over z, negative d y over z, negative d. It's all very simple, but there's a big catch here. But the mapping from u to v is not linear, and it's not affine either. So that's not hard to check, basically because we're dividing by z here. So we need some way to take care of this because we want to have still a 4x4 matrix representing the mapping from u to v. So we still want a 4x4 matrix sending u to v. So we'll see how to do this in the next board. So let me start by copying over the formula for v here so we don't lose it. We have u equals xyz and v equals x prime, y prime, z prime is equal to this. It's equal to negative d x over z, negative d y over z, negative d. And we want a matrix to represent the map from U to V, but it's a 4 by 4 matrix, so it'll be over homogeneous coordinates. So what we do for this is we let U be represented in homogeneous coordinates by x, y, z1. Okay, well, for V, of course, it is represented by negative d x over z, negative d y over z, negative d1. But we want to use a different representation. It is also represented by, and I'm just going to multiply through by z, negative d times x, negative d times y, negative d times z, z. So why does this work? Because as a 4-tuple, this is a homogeneous representation of a point. How do we find the point that it represents? We divide through by the fourth component, which in this case is z. We've always been called w before, but now it's z. So I divide through by z, we get exactly this. So this does represent V. So we're going to use this representation, and we're going to use the following matrix. We'll let M be the following matrix. So it's negative D, 0, 0, 0, 0, negative D, 0, 0, 0, 0, negative D, 1, 0, 0, 0, 0. So something strange has happened here. When we had affine transformations, the bottom row was always 0, 0, 0, 1. Now the bottom row is 0, 0, 1, 0. And also strange is that the last column is all zeros. That actually is due to the fact that the viewer is at the origin. That will not always happen in more general situations, but that is what happens here. So let's see why M works. If I take M and we multiply it by the homogeneous representation for U, that's x, y, z1, that turns out to be, well, again, we're taking the column vector x, y, z1 times this row, inner product of this row, inner product of this row, inner product of this row, and inner product with this row. And what we get is we get minus dx, minus dy, minus dz, z. And that's exactly the representation of V. So we took a representation of U, and we obtained a representation of V. So when acting on homogeneous coordinates, M does take the representation of U to a representation of the correct point V. So M does represent the map from U to V, but it does so over homogeneous coordinates, not over ordinary coordinates. Over ordinary coordinates, it wouldn't be linear. There's no way to represent such a map by a matrix. Over homogeneous coordinates, by being a little clever, we've turned it into a linear map, and then we have a matrix for this. So you might worry here that maybe this has skipped a point, because after all, U has other homogeneous representations, and M ought to work correctly on all of these. Let me rephrase this a little bit. More generally, we might have U has the form x, y, z, w, and so this represents, in R3, x over w y over w, z over w. In this case, the desired v is, let's go back to this formula up here. The desired v was given by this formula when u was given by as x, y, z. Now u is equal to, or represents the point x over w, y over w, z over w. So when we plug those in for the values of x, y, z here, we get still negative d x over z, negative d y over z, negative d. The same point, right? And this is again because the viewer is at the origin. This is why this happens. The w just disappears because the w's have just all canceled out. I had x over w over z over w, y over w over z over w. And so the w's have just canceled out. In this case, now we take M, this same 4x4 matrix, times this new u, x, y, z, w. And well, you can see that, in fact, the matrix is all zeros in the fourth column, so the w has no effect. And it is equal to negative dx, negative dy, negative dz, z again. And this still represents, this is still a homogeneous representation of the desired point v. So in this way, the homogeneous matrix, or the matrix acting on homogeneous coordinates, will work for any homogeneous representation of a point u to give the homogeneous coordinates of the desired point v. Okay, so this is nearly the end of this presentation. I just want to comment at the very end that one thing we did do, the trouble was here that the trouble with this whole discussion is that the depth value is just frozen at minus d. So the depth value here is the z-coordinate is always minus d. It doesn't depend on the distance of the object from the viewer. When we're rendering objects, we want the depth value as written to the pixels on the screen to accurately reflect in some sense, at least in a relative sense, the distance from the viewer. It definitely does not work to just freeze the depth value to a constant because then we lose any information about the distance from the viewer. So we need to fix this. So this needs to be fixed. So that will be done in part 2 of this presentation, which will come after we first talk about shadows. All right, this is the end of the presentation. Thank you very much.